Welcome to today's webinar. The topic today is analysis of induced vibrations in time history analysis add-on in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the content of the website, the German and English webinars, new features, and so on. I will be the moderator today, and my colleague Stefan will do the presentation, and my two other colleagues will answer your questions, but they can introduce themselves.
Hello, my name is Stefan Frenzel, so I'm the co-organizer today. I will present the new add-on time history analysis in RFEM 6. I'm working here since over 10 years at Dlubal in support engineering and of course in the customer support and in the product engineering, of course, for the dynamic analysis modules or add-ons. And that is it for me. So maybe the next one.
Hello, my name is Dina Effler and I work for Dlubal for 5 years now, and I'm responsible also for the development in the dynamic add-ons and in the customer support. I will answer your questions today.
Yes, hello, and I'm Thomas Eichner. I'm now since around about a year at Dlubal Software, and I'm also working with Stefan and Stine on the development of the dynamics add-ons of the program. And I will also try my best to answer all the questions you have today.
Okay, thank you for your introduction. Maybe an additional information from my side. I've been working for the company for 13 years now. Okay, then we can switch off our webcams that the attendees can see the full screen. I say something about how you can ask questions, at least for the attendees who participate the first time. You can show the control panel with that arrow here, and then you can enter a question here, and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, then I hand over the screen to Stefan. Stefan, it's your turn.
So hopefully you can see my screen. Okay, so I will just go on this one. Okay, we go directly to content. So as we said in the introduction, of course, we want to have a look today on the time history analysis on the new add-on. I want to show you, of course, the features of the new add-on time history analysis in RFEM 6. And here's the content for that. So the content is today, I want to give you, of course, an overview over the dynamic analysis add-ons, which we have now in RFEM or in R# 9. Then in the next step, we want to do a natural frequency analysis of a structure with using the model analysis add-on. So this is part, of course, of the dynamic add-ons what we have in the program. We want to do it for a building like this which you see on the screen. So it's made out of concrete and steel. The next step of our example is then that we want to perform a time history analysis, and here with a machine-induced vibration, and therefore we use, of course, the time history analysis add-on to separate the loads, horizontal and vertical loads, and of course, to give them a timestamp at the end to get a result. So when we are done with this, I want to show you how to optimize the structure in the case of resonance of the structure. Okay, so then I'll go on the next one, and here, of course, you see the add-on modules what we have in RFEM 6 and R# 9. So the first one here on the left side is, of course, the model analysis. So this is a basic tool in RFEM 6 to calculate, of course, the eigenvalues of the structure. So you get the equivalent load factor, you get, of course, the eigenfrequencies of the structure, which is a really important tool to do, of course, also the other stuff or the other dynamic analysis, or to use the other dynamic analysis tools. You need, of course, the model analysis. The next one what we released was the response spectrum analysis module or add-on. With this add-on, is it possible to do a response spectrum analysis for in case of earthquakes, for example. It's a linear calculation in this case. Here you can, of course, choose a response spectra according to a design code, for example, the Euro code or the US code or some other codes, yeah, what you want to use. You can also create your own your own response spectras, maybe also out of accelegrams if you want to do this, and then the program will calculate for each FE mesh point internally an equivalent earthquake load, and then you will get at the end, of course, the internal forces for the directions and also the combined reactions of the whole structure. I will go now on the right side because that's the pushover analysis. It's more familiar to the response spectrum analysis because here we are able to do a pushover analysis for structures. Yeah, therefore we can calculate the capacity curve of the structure, and we are able to do we are able to do the pushover analysis then for such a structure with nonlinear hinges according to FEMA or according to Eurocode if you want. Yes, of course, and then you get the response for that, also in the nonlinear case. And the last but not least add-on module is the time history analysis module or add-on. In this add-on, you are able now to combine the times or to combine time with loads and to get a result then out of that. Yeah, and this one we want to do today, and therefore I created a small example. This is here our practical example. It's a machine-induced vibration. So just as an introduction here, that's a normal steel frame structure with the concrete surfaces here on this side. And we have, of course, here a machine which induces a vibration on the structure with a frequency or with a rotationing unbalance of 0.2 kilonewtons and a frequency of 5.6 hertz. And then we want to see what's happened to the structure when we bring the frequency or this load with the frequency on the structure. Therefore, I want to switch to RFEM 6 now. And here in RFEM 6, of course, I opened the structure already. So you can find also, or my colleague Andreas will send you, I think, a link with the structure after the webinar, where you can have a look on that, what we do here today. Here in RFEM 6, of course, you see at first our structure and also some loads here, the self-weight of the structure. And I created also a self-weight of the machine in this case. And of course, I created here some horizontal induced load and a vertical induced load. Yeah, that's this one and this one. I will show you later how to calculate this or how it comes to this. Yeah. But in the first step, we want to do, of course, a model analysis for this structure. And therefore, you are able here in the program to go in the base settings of the of your file, and in the base data you are able to activate add-ons. In our case, we want to activate the add-on for the dynamic analysis. Here in this case, of course, model analysis and of course the time history analysis, because we want to use them afterwards also. You see that in RFEM 6 you are able to activate different add-on modules, yeah, of course for analysis or for dynamic analysis, or of course for design of structures, for example for steel or concrete. Yeah. So and here you're able to solve this or to switch it off and on here in the add-on tab in the base data of the program. So in our case, we want to do this, and we say okay. And now we want to do a model analysis for our structure. How we can do this easily. So that's the first question. Therefore, I go here in the load cases and go at first on edit. You see that we have here 4 different load cases. for my model analysis, normally I need 2 load cases. That makes it a little bit different, because here I have to create now at first a load combination to assign, of course, these 2 load cases. Here I want to assign load case 1 and load case 2, because in this case I want just to have a look on this, or on the eigenvalues of the structure when the self-weight of the structure and the self-weight of the machine is available, and therefore I took these 2 load cases for that. It's not necessary to choose here another static analyzer setting, because for the model analyzers we just use the masses which are here in vertical directions or in Z direction for the model analyzers. So therefore we can go back to the load cases, and here we create for us a new load case. It's load case number 9 here now. And if you want to perform a model analysis in the program, you just have to switch here the analysis type to model analysis. Yeah. So if you switch this to model analysis, you will have, of course, a new option, which are the model analysis settings. And of course, the program wants to know which self-weight or which load should be used for the model analysis. Yeah. So if you have here a load case with loads in it, then the program will calculate automatically the loads into masses. But it's also possible to create masses in the load cases, and then you can use, of course, these masses. Here in our case, we want to use the load case load combination number 1, which is made out of load case 1 and load case 2 together. And these masses we want to use now for the model analysis. Here I just have to go in the model analysis settings, because for these model analyzers I need a number of modes. It's not 4, it's 30. So I need 30 eigenmodes for the calculation. So I know this because I did it before, of course. Yeah. Otherwise, you have to choose your own value, or you have to prove it, of course. So the mass matrix should be consistent. That means the masses are separated on the members via a function. That's normally the best way to do this, because it's the best way to consider the masses exactly on the structure. Then we can click here on OK, and we can do, of course, a calculation. Now you see the program will, of course, mesh the structure at first, and then the program will calculate load case number 9. So it's not necessary to calculate the load cases 1, 2, or the load combination, because we just took the masses from these load cases or load combinations. So our first natural frequency you can find here on the navigator or on the result navigator. Here, of course, you can switch to the eigenvalues. But here's a really good eigenvalue. It's also 5.6 hertz. It's like our induced vibration, and you can see, of course, the structure will move here in x direction globally. Yeah, that's normally not so good when you get this. Yeah, because in this case, I will go back, or I will switch back to the presentation. In this case, we have, of course, we have to define now the input values for the time history analyzers. And I told you that we have, or that we want to use 0.2 kilonewtons, yeah, as rotational mass, and or as unbalanced mass of the machine. And I have to calculate these 0.2 kilonewtons to the member length, and then we get 0.025 kilonewtons per meter. And this I bring here on the structure and the load case number 7 and 8. You see here the 0.05, and here also I just divided it by the member length, where the machine stands on, and then I calculate this value. So if I go back to the input values. So I have to define now two diagrams. So one for the horizontal and one for the vertical. And for the horizontal and the vertical, the difference between is just a shift of p.5, yeah, and that's all. In this case, you see that we have, of course, by the rotation of the mass, I have a vertical maximum load and a horizontal maximum load, yeah, and it's described by a circle. So that means I have to use a sinus function for that, yeah. As you know that we have, or I said that we have 5.6 hertz as induced vibration. So these 5.6 hertz, I just have to calculate to the to 35.2 rad per second, yeah, because this value I need, of course, for the input of the function or of the time function. So, but how we can perform now here a calculation with the time function. If you activate it, like here in the base data, the add-on time history analysis, you will find here in the dynamic loads, in the navigator, in the data navigator, of course, one which is called time diagrams. And here, of course, you can create your time diagram. This time diagram means, okay, or you have to multiply this time diagram then with the load, yeah, from a load case, and then you are able to go through the loads by times, yeah. Therefore, you can say, okay, we want to have a user-defined time diagram. That means you have to type in, of course, the time and the multiplier for that. That makes normally not so much sense. The other thing is that we can use, of course, a function. And here in our case, we want to use, of course, the function because it's a really easy function. It's just the sinus of 35.2 multiplied with the time. Yeah, that's all for that. And then you should get, of course, here the result for it. Yeah, so that means we want to get a sinus function. Here in this case, we don't call it function. I just want to call it horizontal part. Sorry, there's an R. Oh. Like this. And of course, I copy the whole function again. And here I say just, okay, I just add here the value 1.5708 to get the switch here, yeah. And I will just change the name to vertical part, yeah. Vertical part, yeah. So, and these two functions describes the induced vibration of my structure, yeah. Nothing else is it. So, and here you see, of course, the switch between. So here we start with a maximum, and in this one we start with 0, yeah. And that's the same like I do it. I have here, if I go to my circle here, when I have here a maximum load or a maximum force, then the force in the other direction is 0. And if I rotate more and more, so 90 degrees, then the other one is maximum and the other one is 0. Yeah. Therefore, I use here the function to show it or to get, of course, the same behavior like this. Yeah. Like in my presentation. Yeah.
Sorry for the interruption. In the PowerPoint, you used 35 rad, and in the
oh yeah, that's correct. 35, yeah. So it was just that was my fault. Yes, yeah, it was just a typing error from my side. I have it also on my letter here, 35.2. Okay, thank you for the interruption. Okay, then we can go on. Okay, I changed to the value 35.2. So at the next step is just want to show you that we have here the angular frequency also of 35.4. So it's near to 35.2. That means for me, so it could be that I get here a resonance for the whole calculation if I do this, yeah, because the horizontal part here, yeah, it's like this. That's my horizontal load. And if I have a look on this eigenvalue 35.2, I have just to go to load case number 9. Then I see, of course, a deflection, which is also in the x direction. And that means normally for me, okay, you have to be careful. Here could be, of course, a resonance in the structure. Yeah. Okay. So with this knowledge, we go now to the calculation of the time or of the time history analysis to show, or maybe we don't see this, but hopefully we can see this, that there's a resonance in the structure. Therefore, we have to create here a new load combination. And in this new load combination, we are also able now to change the analysis type to time history analysis. That means for us, of course, that we are able now to assign load cases, yeah, and these load cases, therefore, we are also able to assign to this load case a time diagram. And now here we have, of course, that's of course our input for that. Yeah, that means we have a horizontal load with a time diagram, and we have a vertical induced load with a vertical part of the time diagram. And that's normally all for that. Yeah. So because now we can induce the machine load or the machine unbalanced load to the structure over the time. So we just have to change some time history analysis settings, yeah, because here we want to use the linear model for that. Yeah, the damping should be 0. We don't need a damping at first time. Our maximum time, it's okay when we take 5 seconds for that. Yeah. The split safe time steps should be 10. That's good, a good value, and that's normally all for this one. Then we can say here, okay. And if I use, of course, the linear model analysis for the time history analysis, then of course I have to choose here the result of a model analysis. That means for me, I just have one load case with a model analysis, so I can just use this one. And then we can click on OK and calculate the whole stuff. The program will do now, or will perform now, the time history analysis over 5 seconds with a delta t of 0.01 seconds. So there will be created a lot of results, of course, but it's here in this case necessary because I have 5.6 Hertz as induced vibration, and therefore I need, of course, a small time step. So, okay, 35 seconds, it was not so long. Okay, so what's the result of that now? Yeah, so the results are also like in RFEM5 or like in the old program. You get the results here as a summary in the global table of the structure, and maybe some of you know or used the old one, and here it was possible to create also directly a diagram. So because it makes now sense to have a look on a diagram, because here I can't see anything. Yeah, so I can of course switch here through to my time steps, but it makes not so much sense because I need normally, or I pick normally one point and I want to see this point over the time. What's happened to this point? Yeah, and therefore we have here calculation diagrams, which you can find in the navigator data on the data navigator. If you just click here on the new calculation diagram, you will be able to say, okay, you want to have a basic diagram, yeah, 2D. We want to have a diagram from the time history analysis, load combination number 2. That's correct. And here, for example, I want to have a look on the nodes accelerations. That makes normally sense. So I take this one, okay, and I just have to click on a node. Maybe I want to have a look on this node. That looks not so nice. Maybe we take this one. No, wait, X. X looks nice, yeah. So the X direction. The other one, this one here, it's made out of all directions. Therefore, it looks a little bit strange, yeah. But in our case, we should have a look on the x of the acceleration in x direction, and here we can see, of course, a nice picture of a resonance calculation. Yeah, that means the resonance is really high. So we will get here, of course, a resonance in this, or we will get a resonance in the structure, and maybe that's not so good because now our structure can get a failure by this. Yeah. What we can do now is, of course, we can create, or we can go to our load combination number 2, and can say, okay, normally if I do a time history analysis, there is also a damping. Yeah. Here in our case, if we want to, or if we use the model analysis type or the linear model analysis for the time history analysis, we are able to use the layers damping. And here I want to get, or to use damping of 0.02. If I use here not the linear, if I use here the linear implicit Newmark solver for that, and then I'm just able to use here the relay damping coefficients. Therefore, I have to calculate them at first. Yeah, this is more easier because you find it also in the literature. You find damping values or layers damping values for structures made out of steel or concrete. Yeah. In our case, we want to use 2% of that, and then we just have to recalculate the whole stuff. So that means for us, we just calculate load combination number 2 again. And then we will hopefully get, of course, here also a result. So, okay, now we are nearly ready. Okay, so we see that we see nothing. So really, yeah, so that's why we go back here in the time on the calculation diagram. And within the calculation diagram, I see now here a maximum of 0.24 meters per square second. That's of course a high value, yeah, and that could be now that, of course, also by using the damping, that it's not sufficient for us or for using the whole building like this, yeah. So, and now we come to the point where we have to optimize normally the structure. So one optimization could be we use another machine, yeah, because if we have another induced vibration, then maybe it could work, yeah. But normally, it's also possible to change something in the structure. Yeah, here in this structure, I want to change the bracings because here maybe I took here another axial stiffness for these ones. Then of course the eigenvalues will change of the structure, and hopefully it's then possible to use, of course, the same machine for that, maybe with another bracing or another cross section type for that. Yeah, but how we can perform such an analysis? So therefore, we have to go at first in the special objects. In the special objects, we are able to create here a structure modification. A structure modification could be here for sections. Yeah, in our case, we want to change the sections, and we know that our HAA 100 is here the bracing. Here we want to use, for example, double time stiffness of the area. So, or we want to use the double area for that. So that means for us, of course, the actual stiffness will be doubled. Yeah. And another option could also be that we copy the structure modification and say, okay, hey, maybe we take just the half of the stiffness for that. Yeah. Could be also an option for us, because an HEA 100 is maybe not so, maybe it's also too big, this cross section type, yeah, in this case. So here we created now 2 structure modifications. So I will change the name here to, I will call it double stiffness. And I will call this here half stiffness. And that's all for us, yeah. And now I want to consider this double stiffness or this half stiffness to the calculation of the time history analysis. So therefore, I have just to edit my load combination or my load cases, because here for my load cases, I have to consider now also the stiffness modification. That's also really easy, because here I just have to copy the load case number 9 to load case number 10, and here I want to have the structure modification double stiffness. Then I copy it again, and here I take, of course, the half stiffness of that. Yeah, that's all for it here. For the load combinations, of course, I have to do the same. Therefore, I can go here in the load case or in the load combination. I just copy the load combination, say, okay, here I want to have load case number 10. If I choose here load case number 10, the program knows that in load case number 10, a structure modification was used. And therefore, the structure modification is also used here in this load case number 10 again. If I copy this load combination again and say, okay, here I want to use 11, then the program will automatically take the half stiffness, because this one was used in load case number 10. Load case number 11, sorry. Okay, and that's all. Now I can go on calculate. So you saw that the program will calculate at first load case number 10 and 11, because they are essential for combination number 3 and number 4. So it's not possible to calculate load combination number 3 and 4 alone, yeah. So therefore the results has to be at first calculated, and this was done in load case number 10 and number 11. Okay, then the program will do the calculation. I think it will not take so long. Okay. And now we have the results here, yeah. So then maybe we can have a look on that at first. Therefore, we can go to the result diagrams and can edit them, of course, yeah. So we see that we have at first we do the we had a look on load combination number 2 for the acceleration in x direction at node 43, and here we get, of course, a high acceleration for that, yeah, caused by the resonance of the structure. Then I will just copy the load this time diagram or this calculation diagram, and here I will just choose combination number 3. And if you see that we, so I choose now combination number 3, and you see that we have here at the beginning, of course, it's the beginning of the induced vibration, and after this beginning, the structure will vibrate with a constant or with constant values normally. But you see that the accelerations are really small, yeah. They are so small, it's not possible to have a look here directly on them. So it's normally nothing. So this is the result when I do it here with the double stiffness of the bracings. If I use here, of course, the half stiffness of the bracings, then the result looks like this. So that means for me, if I use, of course, smaller cross sections for the bracings, I get, of course, an acceleration in this case, which is also really small, 0.03, instead of 0.2 meters per second. And therefore, of course, you can also choose maybe a smaller cross section or a bigger cross section. That depends, of course, on you and maybe also on the stress level of the structure. But normally these bracings, yeah, they could be normally really small, because you just need the actual forces in it, or you just have normal forces in these bracings because they are hinged at the start and at the ending, and therefore is it normally not so necessary to use big cross sections, yeah. So in this case, just by changing the bracings, you will be able to work also with this machine on this structure, because the induced vibration of this machine is then not necessary anymore for the structure. But it's always good to have a look on such things, because here, of course, nobody could notice that we get, of course, here an induced or a resonance case, like here for such a machine when I put it on the structure. Yeah? And therefore, yeah, you can design, of course, such a structure just by choosing other cross-section types or using here the structure modification to get, of course, a result for the structure which is usable at the end. Yeah. Okay. Andreas. Are you there?
Sorry, yeah, I had to unmute
okay.
myself. Yeah, thank you for the presentation. I hope yeah, it's clear now. But yeah, we present also on our website the recording in the next days, and you can download the model, as you already said, and the PowerPoint slides. I would like to show you where you can find all. I can take over the screen. Just a moment. So before I go to the website, yeah, just a small hint. If you want to get the free online product demonstration, for example, for the dynamic programs or add-ons, or the program RFEM or RSTAB itself, yeah, then just contact our sales team with that link here or the QR code. You can also get the non-binding offer, yeah, if you want. You can download this PowerPoint slide from our website, as I already mentioned. I go to the website before I close the webinar. Dlubal.com is our website, and under news and events, you can find the webinars. This is today's webinar. Those are the webinars of the next week or weeks. Wind, the FRQ webinar, then a quite interesting webinar, how to integrate artificial intelligence to RFEM using API. Yeah, if you are registered for our newsletter, you will get an invitation. So I click on today's webinar. Yeah, you will get an email directly with a link that leads to that page here. Then you will find the recording here in the middle. Then you can download the presentation slides. They are already online, and you can also download the model. Okay, that's also all from my side. Oh, it's a little bit dark, sorry. Yeah, thank you for your attention. Thanks to Stefan for the presentation. Thanks to my two other colleagues, Stine and Thomas, for answering the question or questions. There are maybe 10 questions or so. Okay, they are answered almost all. Yeah, something are not answered. Yeah, you will get an email in the next days. Okay, I wish you a nice rest of the day, and bye-bye.